Okay, let's look at the proof of the root test. We have three cases. It says that if the limit of the nth root is some value L less than 1, then the series converges absolutely and therefore also convergent. If it's greater than 1, then it is divergent, and if it's equal to 1, it's inconclusive. So let's look at case 1. So again, if the limit of the nth root of a sub n is L in absolute value, that means I have some L value that all of these guys go to after some value n greater than capital N. So again, eventually all these guys are going to lie in a window around L. How close around L? As close as we want it to be, depending on how large we want to take n. So again, nth root of a sub n, after some point, all of these guys are going to lie in that little strip and huddle around the limit that they go to, which is L. So they will be within an epsilon strip to the left and to the right of the value of L. And since L is less than 1, we make a note of that 1 is over here and L is somewhere here, and we've chosen a little window around it so that our window stops before 1. And we can do that because the larger I take n, the closer I'm going to huddle around this L value. So that's up to us. And we're going to call this guy at this end maybe some value R. So we can say that the nth root of absolute value of a sub n will always be in 0 somewhere here, let's say. Positive, because I'm looking at an absolute value, of course. And all of these guys, for some n greater or equal to n, all of these guys are going to be less than R. We can do that. We can say that's less than R because they're going to get closer and closer to L. So what I have here is that basically an absolute value, a sub n raised to the 1 over n, is going to be less than R. And I can go ahead and raise both sides to the nth power. So when I raise the left side to the nth power, I get a sub n in absolute value. And when I raise the right hand side to the nth power, I get R to the n. But we know that this guy, R to the n, makes actually some, this is a geometric, we know that this makes a geometric series because all the terms are R times R times R times R, so on, when I go to the right. This is a geometric series, and since we know that our R chosen was less than 1, it has to converge. So this guy, all of these guys are bounded by R to the n, and R to the n makes a geometric series that's convergent. So we can say, by the comparison test, which we called CT, we also have that these guys from that capital N on location also converges. We can go further and say, I started at capital N, but had I started at 1, that would still be okay because we know that a finite number of terms don't affect convergence and divergence. So now basically what we have, that the series converges absolutely. So all of this converges, which means all of this converges, and since I had the series looked at in absolute value, this is actually an absolute convergence. So this says that a sub n absolutely converges because I've shown that it converges in absolute value, which implies that a sub n itself converges, just a simple convergence, because we had shown and proved before that absolute convergence automatically implies regular convergence. So we are done with case 1. Let's go look at what case 2 says. So all we did in case 1 was compare the geometric series that converges. Case 2 says that if the limit is bigger than 1, then the whole thing diverges. So again, we're going to look at all the nth root of a sub n terms going to this value L that they're supposed to go to. So all these guys go to L, and for some n greater than capital N, we can create a small window around L that all these guys belong to. So eventually all of those guys huddle around L, right near it, as near as they want to. And we also know that this L that they go to is actually bigger than 1 in this case. So let's say 1 is over here, we got 0, we got 1, and then L lies somewhere to the right of 1. And we ensure that this guy is in between 1 and L by just choosing our n sufficiently large enough so that all the guys huddle close around L away from 1, and we can say, let me call this guy some value r, so that r is in between 1 and L. So that all these guys that huddle around L are actually going to be closer to L, bigger than this r value, which is actually bigger than 1. So what I have is absolute value of a sub n really raised to the 1 over n greater than r, which actually is greater than 1. I keep that in mind. Now if I multiply, or if I raise both sides to the nth power, I have raised this side to the nth power, the 1 over n goes away, raise this side to the nth power, and I have r to the n. Now if I look at the limit of these guys as n goes to infinity of both sides, I know that this guy right here has to become infinite, since we had chosen r to be bigger than 1. And remember, we talked about r to the n, when r is bigger than 1, it just blows up and becomes infinite. Well, if that's the case, and this blows up and becomes infinite, then I must have that this guy also becomes infinite. So the limit as n goes to infinity of a sub n in absolute value goes to infinity as well. So then that implies that the limit as n goes to infinity of a sub n then cannot possibly be 0. Because if it did, its absolute value terms, their limit would go to 0 as well, and it doesn't in this case, it goes to infinity. So now we can just quote the divergence test, because the divergence test says if the limit of the terms don't go to 0, then the whole thing automatically diverges. So by the divergence test, the series diverges. I started it at 1 because, again, as we said earlier, a finite number of terms from the beginning to the capital N value does not affect convergence and divergence. So when the limit is some value bigger than 1, we can conclude that the whole series diverges. Last case says, similar to what the ratio test said, it says that if the limit goes to 1, then we cannot really use the root test. It's inconclusive. Let's go look at an example of why that happens. So the limit exactly equal to 1, inconclusive. Let's look at our favorite quick series that we know some info about, the harmonic series. We know this guy diverges because it's a harmonic series. We proved this a couple of ways. Now let's go apply the root test on it. Take the limit of a sub n in absolute value. It's nth root. All the terms are positive, so I can get rid of the absolute value also if I want, and I end up with 1 over n raised to the 1 over n because I'm looking at the nth root. Well, that'll be just the limit as n goes to infinity of 1 over n to the 1 over n. Top and bottom share that exponent. We said in class that this guy is going to go to 1 by using L'Hopital rule, and we can go ahead and quote that without having to show why that happens every time. So this is going to go to 1. So the series diverges, but the root test takes me to 1. Let's look at another one. We know this series is a p-series, similar to the p-series with p equals 1 for the harmonic, p equals 2. This guy we know converges. Let's use the root test on it. So we take the nth root of a sub n in absolute value. Since they're all positive, I can get rid of them again. So I have 1 over n squared to the 1 over n. That's going to get me to 1 in the numerator over n squared to the 1 over n. I could do some algebra on this and say n squared raised to the 1 over n. I can multiply the exponents if I want and have that be n to the 2 over n, and then rewrite it so that it looks like this guy over here. So we're going to rewrite as 2 over n as 1 over n squared, or looking over here, we just switch their roles since we're going to multiply the two exponents anyway. And again, based on the fact we accepted and showed in class, this guy goes to 1, so I have the limit 1 over 1 going to 1 also. So I had a divergent series using root test going to 1, and I also had a convergent series using the root test going to 1, so therefore the root test is going to be inconclusive. Because in using it, either one can happen. You can either get convergence or divergence if you end up with a 1 for your root test. So when that happens, of course, go analyze it some other way using some other test.